Hello everyone and welcome back to a fairly brief video today. I'm not going to be solving this puzzle today, but I'm going to explain to you a very interesting piece of logic that you can use to start this puzzle. I did actually try this morning. It was on Cracking the Cryptic as a featured video, and I got quite a way through this and before eventually getting stuck and had no idea how to continue. And I went back to Cracking the Cryptic and had to watch, and Simon clued onto something really quickly. A trick that you can do that's fairly surprising when you see it, but which helps to start the solve, or in my case it would have helped to continue the solve partway through. And so I'm going to show you how this works. Now this is a puzzle by the famous Wetering, an absolute king on the world Sudoku scene, featured on Cracking the Cryptic many times, and is responsible for the video of theirs which has 7 or 8 million views, the most watched Sudoku in the history of the universe, and renowned for building puzzles that have very straightforward rule sets, very minimal kind of starting points, and just really classy stuff. So this one is called Where is the Eighth, and the name is important in this, which I'll explain. Just to explain the basic rules of this puzzle, the digits 1 to 9, like in any Sudoku, must appear in every row, column, and 3x3 box. And in addition, we have these arrows. And what an arrow is, whatever's on the arrow, we'll say this was a 1, 2, and a 3, say it was that, then this has to just be the sum of those digits. So it would be a 6. And if that was a 4, that would be a 7, etc. So that's all the arrows are. And there was another rule, but it's not important for the purpose of this demonstration. If you are wanting to try this puzzle, I'll put a link to it. Just make sure you read the rules, because there's an additional rule at play as well. Now, as for this trickery, I was surprised that Simon thought of this so quickly, because I started just solving it in a fairly normal way, whereas Simon clued on early on that there was something potentially a little tricky happening here that was worth investigating. And in particular, he thought, well, the title of the puzzle is Where is the Eighth? And what is that hinting at? And if you look closely, you'll discover that there are 7 arrows in the grid. And so you might think, well, where's the 8th arrow? Are we supposed to identify an 8th arrow somehow? It's not stated in the rules that we need to do that. And I suppose probably technically you don't have to, but I think because the point that I got to with the puzzle, I don't think there was really any straightforward way forward without having done this trick here. And this is really, it's quite astonishing the way these things work. So this is an example of something called set theory, which is a way of making deductions about a grid that involves kind of comparison of different sets of digits. And so I'll explain how this one works. What we're going to do is we're going to select the 4 boxes in the corners. We don't know exactly where the digits are in them, but we do know for certain that they do contain the digits 1 to 9, each of them. So we've got 4 sets of the 1 to 9 selected in blue. And now I'm going to say, what if I took another 4 sets of the digits 1 to 9, but in a different configuration? So let's say I took the top row and the column here, and this row, and then the first column. And I said, that's also, that's also 4 sets of the digits 1 to 9, and I'll give them the color yellow. Now, when I did that, these corner cells actually I have to count them twice, because let's say that was a 7, that would be in this set, and it would be in this set. So there's 2 of that one. So these corner cells each have 2. So we'll make that, give that yellow as well as orange, just to say that we've got 2 yellows in there effectively. And what we know now is that the blue digits are 4 sets of the digits 1 to 9, and the yellow and the orange sets are 4 sets of the digits 1 to 9 as well. Then we can start looking at individual cells that are in 2 colors and say, whatever this digit is, we don't know what it is, but if we removed it from the yellow set and from the blue set, so we just delete the colors, the blue set and the yellow set are now still the same. They're no longer 4 sets of the digits 1 to 9. They're 4 sets of the digits 1 to 9 minus that particular cell, but they're the same as each other. we can do this for all of the cells that have two colors. So let's do that. And these ones in the corners, they were blue, so we can remove their blue, and they were two yellow, which I indicated with yellow orange. So now if we take away the blue and we take away one of the yellows, we're left with just the one yellow. And now we can say that the sets that we've got here are equivalent. Again, we don't know what digits they are, but all we've done is taken the same digits out of both of the sets. So now the blue digits all exist in the yellow digits. Now, we can make a further deduction based on these arrows, because let's say this was a 9 and this was a 2, 3, 4. If I removed this cell and I removed its equivalent sum here, so I take out the yellow 9 and the blue 2, 3, 4, the sets are no longer the same numbers because I took out a 9 from yellow and I took out a 2, 3, 4 from blue, but the sum of each of these sets is still the same because I took 9 out of yellow and I took 9 out of blue in terms of its total. And I can do this for each of the arrows. So with each arrow that I remove, all I'm doing is taking the same sum out of each set. So if I do this all the way around the grid, we get this. Oh, sorry. And now we know that whatever's left, this one yellow cell has the same total as these blue cells. And so this is, in effect, our 8th arrow. That behaves, whatever's in this cell is the sum of these 3 cells, which is exactly how arrows work. And indeed, it completes the symmetrical arrangement of the grid. And from here, we can make, we know this is at least 1, 2, and 3. So this has got to be a 6, 7, or 8, or 9. And we can continue on with our solve from there. Surprisingly, this puzzle could be, you could get quite far in this puzzle without making this deduction. But as I said, the point that I got to, I don't think there was any trivial way of continuing unless you knew that this relationship existed. So there you go, a little bit of a variant Sudoku magic. And this idea of set theory is something that's really only cropped up in the last 2 or 3 years since Cracking the Cryptic started publishing so many puzzles and bringing so many people into the Sudoku community. And some very clever folk did some thinking about these kinds of relationships. Notably, Fistemafel is a setter who has given whose name has been given to a theory called the Fistemafel theory, which is basically was kind of the genesis of all of these kind of set tricks. And I'll put a link in the description to a video that was done on math on Numberphile a little while back, where they interviewed Simon from Cracking the Cryptic, and he explained the Fistemafel theory, if that is interesting to you. So thank you very much for joining me for this. I hope that was an intriguing introduction to some of the wizardry that exists in these puzzles. And unfortunately, I couldn't solve this myself on video, but no doubt there'll be another one soon. Until then, take care, and I'll see you soon.